Picture this: a beam of light races across the cosmos, covering the distance from Earth to the Moon in just over 1 second. Yet even at this staggering speed, light is too slow to reveal the universe's deepest secrets in a single lifetime. What if I told you that light's speed, the ultimate cosmic speed limit, is both a ruler and a prison for the universe? From black holes bending light into oblivion to galaxies fleeing faster than light itself, the universe is filled with extremes that defy common sense. Today, we're diving into 50 mind-bending facts about light speed, phenomena so extreme they'll make you question reality. Why does light slow down in water but never in a vacuum? How can the universe expand faster than light without breaking the rules? And what happens when you approach light speed and time itself begins to warp? Stick around, because by the end of this journey, you'll see the cosmos in a whole new light, where the impossible becomes inevitable and the ordinary transforms into the extraordinary. Ready to have your mind stretched like space itself? Let's begin. Now let's shatter a common misconception: light doesn't always travel at the same breakneck speed we associate with it. While it zips through the emptiness of space at roughly 299,792 kilometers per second, light actually slows down when it passes through materials like water or glass. This happens because photons, the particles of light, interact with atoms in these mediums, causing tiny delays as they're absorbed and re-emitted. The measure of this slowdown is called the refractive index, a number that tells us how much a material bends and retards light. For example, water has a refractive index of about 1.33, meaning light travels around 25% slower than it does in a vacuum. This bending effect is why a straw in a glass of water appears to snap at the surface, and it's also why telescopes must account for Earth's atmosphere distorting starlight. Even more fascinating, astronomers use this principle to study distant objects. When light from a quasar passes through interstellar gas clouds, its speed changes subtly, leaving fingerprints in the spectrum that reveal the cloud's composition. So next time you see a rainbow or glare on a wet road, remember, you're witnessing light's speed shift in real time, proving that even the universe's fastest traveler isn't immune to a cosmic speed bump. Now let's tackle one of the universe's strictest rules. Light speed in a vacuum isn't just fast, it's the ultimate speed limit. Thanks to Einstein's theory of relativity, we know that nothing with mass can ever reach or exceed 299,792 kilometers per second. Think of it like cosmic traffic enforcement. No matter how much you press the accelerator, your spaceship's speedometer will inch closer to light speed but never quite hit it. The reason, as an object approaches light speed, its mass effectively becomes infinite, requiring infinite energy to go faster. It's like trying to push a shopping cart that magically gets heavier the faster you run. Eventually, you'd collapse from exhaustion before breaking the barrier. Even hypothetical scenarios fail to cheat this limit. Imagine a futuristic train racing alongside a light beam. No matter how fast the train goes, the light still zooms ahead at the same unshakable speed. This isn't just theory either. Particle accelerators like the Large Hadron Collider hurl protons to 99.999999% of light speed, but that last fraction remains untouchable. So while science fiction loves to dream of warp drives and hyperspace jumps, the universe's speed limit is one law even the most advanced civilizations would struggle to break. Here's the next fascinating twist in our journey through light speed's extremes. Time itself bends to its rules. Picture this: identical twins. One stays on Earth while the other rockets through space at nearly the speed of light. When the traveling twin returns, they'd be younger than their Earth-bound sibling. This isn't science fiction, it's Einstein's time dilation in action. The faster you move, the slower time ticks for you relative to someone standing still. At light speed, time would effectively stop, though reaching that speed is impossible for anything with mass. This mind-bending effect isn't just theoretical. GPS satellites orbiting Earth actually experience time slightly faster than we do on the ground because they are moving at high speeds and experiencing weaker gravity. Without adjusting their clocks for this tiny time shift, your navigation apps would be off by kilometers within minutes. Now imagine the implications for interstellar travel. A crew journeying to a star system at 99% light speed might age only a few years while centuries pass on Earth. It's a double-edged sword. Humanity could reach distant worlds within a lifetime, but returning home might mean finding a completely unrecognizable civilization. This cosmic quirk doesn't just challenge our intuition, it reshapes how we dream of the future. And speaking of reshaping reality, wait until you hear how the universe's expansion plays by its own light speed rules. Here's something to wrap your head around. Every ray of sunshine you feel right now is already 8 minutes old by the time it touches your skin. That's how long light takes to race from the sun to Earth, covering nearly 150 million kilometers at that blistering speed. To put that into perspective, if the sun suddenly blinked out of existence like a cosmic light switch, we wouldn't even know for those full 8 minutes. Life on Earth would carry on, blissfully unaware, until the sky went dark and gravity's grip vanished. This delay isn't just a fun thought experiment. It has real consequences for how we monitor space weather. Solar storms, those violent eruptions of charged particles from the sun, also travel at speeds close to light. But here's the catch. By the time we see the flare erupt on the sun's surface, we've got mere minutes before the storm's effects slam into Earth's magnetic field. Satellites like NASA's Solar Dynamics Observatory act as early warning systems, giving scientists a critical heads-up to protect power grids and astronauts from radiation. Even our daily tech relies on this cosmic timing. Ever noticed your GPS acting up during strong solar activity? That's because those storms distort Earth's ionosphere, slowing down the signals satellites send, signals that, ironically, already had to account for light-speed delays just to reach your phone. So next time you bask in sunlight, remember, you're literally soaking up history. And speaking of cosmic time capsules, wait until you hear how the universe's expansion defies even light speed limits. Now here's a cosmic curveball that bends the rules. While nothing can outrun light within space, the universe itself has no such limits. Picture this: the fabric of space isn't just expanding, it's accelerating, stretching galaxies apart like raisins in rising dough. And here's the mind-blowing part. Some of those galaxies are being carried away so fast by this expansion that their light will never reach us. That's right, dark energy, the mysterious force behind this acceleration, is essentially pushing entire galaxies beyond our cosmic horizon at speeds faster than light. But wait, doesn't that shatter Einstein's rulebook? Not quite. Relativity's speed limit only applies to objects moving through space, not to space itself stretching. Think of it like a treadmill. If you're walking at your top speed, you'll never outpace the belt. But if someone keeps cranking up the treadmill's speed, the distance between you and the far end grows faster than you could ever walk. That's what's happening on a cosmic scale. Space is the treadmill, and galaxies are just along for the ride. This runaway expansion has eerie implications. Over billions of years, distant galaxies will vanish from view entirely, their light redshifted into oblivion. Future astronomers might peer into the sky and see only darkness beyond our local galactic neighborhood, with no clue that a vast universe once existed. It's a humbling reminder that even light, the universe's ultimate speedster, can't win a race against the stretching cosmos. And speaking of cosmic races, let's talk about the time scientists thought they'd caught a particle breaking light speed. Now here's a scientific drama that had physicists on the edge of their seats back in 2011. The opera experiment made headlines with a bombshell claim. They detected neutrinos, those ghostly subatomic particles, arriving 60 nanoseconds faster than light should have traveled the same distance. For a brief moment, it seemed Einstein's cosmic speed limit had been shattered. The internet erupted with wild theories, from hidden extra dimensions to flaws in relativity itself. But science has a built-in referee peer review. When other labs tried to replicate the results, the plot thickened. The original team discovered two critical issues. A loose cable caused timing errors, and a misaligned clock skewed the measurements. Once fixed, the neutrinos fell back in line, obeying light's speed limit after all. This episode wasn't a failure, it was science working as it should. Researchers dared to question, the community scrutinized, and the truth won out. It's a reminder that even false alarms push us forward, sharpening our tools and tightening our methods. And while neutrinos didn't break light's record, they did something just as valuable. They proved science's ability to self-correct. Now, let's turn to a place where light's speed truly meets its match. The edge of a black hole. Now imagine a place so powerful that not even light, the fastest thing in the universe, can break free. This is the reality at the edge of a black hole, where gravity becomes an inescapable trap. The boundary marking this point of no return is called the event horizon, a one-way door where anything that crosses, including light, is pulled inward forever. To picture this, think of a river flowing toward a waterfall. The event horizon is like the edge where the current becomes too strong to swim against. No matter how fast light tries to escape, the black hole's gravity drags it back like a cosmic whirlpool. Simulations show this dramatic fate in action, with swirling accretion disks of superheated gas and dust spiraling toward oblivion, glowing fiercely as they vanish beyond the horizon. What makes black holes truly mind-bending is how they warp space and time itself. Near the event horizon, time slows to a crawl from an outside observer's perspective. A beam of light trying to flee would appear to freeze at the edge, stretched and reddened until it fades from view. This isn't just theory. Telescopes have captured the eerie shadows of black holes, confirming Einstein's predictions. So while light may rule the cosmos as the ultimate speedster, even it must bow to the dark might of a black hole. Next, we'll explore a phenomenon that even Einstein found unsettling: spooky action at a distance. Now let's step into a realm of physics so strange that even Einstein himself called it spooky action at a distance. Quantum entanglement is one of the universe's most baffling phenomena, where two particles become mysteriously linked, no matter how far apart they are. Change one and the other instantly reacts, even if they're separated by light years of empty space. Here's the wild part: this connection defies our everyday intuition about how things should work. If you measure the spin of one entangled particle here on Earth, its partner on the other side of the galaxy will mirror that spin in the same instant, faster than light could ever travel between them. At first glance, this seems to break Einstein's cosmic speed limit, but there's a crucial catch. While the particles communicate instantly, no actual information is being sent. Imagine two coins that always land on opposite sides when flipped, no matter where they are. You can't control which side comes up, so you can't use them to send a message. That's the key. Entanglement preserves relativity because it doesn't allow faster than light communication. It's like a cosmic magic trick where the outcome is perfectly synchronized but utterly random. Scientists have tested this repeatedly, even sending entangled particles between satellites and ground stations, and the results always confirm the spookiness. So while entanglement bends the rules of locality, it doesn't break the ultimate law. Nothing outruns light when it comes to sending meaningful signals. Up next, we'll tackle the frustrating reality of light speed's limitations when it comes to chatting with distant stars. Now let's shift our focus to a very real challenge that light speed imposes on our cosmic ambitions: interstellar communication. Imagine trying to have a conversation where every reply takes hours or even years to reach you. That's the frustrating reality of chatting with our farthest robotic explorers like the Voyager probes. Voyager 1, humanity's most distant spacecraft, is so far away that signals traveling at light speed take over 21 hours just to reach it one way. That means if engineers send a command today, they won't know if it worked until tomorrow, and that's just within our own solar system. Now picture trying to talk to a star system light years away. A simple hello to Proxima Centauri, our nearest stellar neighbor, would take over 4 years to arrive and another 4 years for a reply. This delay isn't just an inconvenience, it reshapes how we think about exploring the cosmos. Robotic probes like Voyager or the Mars rovers have to be semi-autonomous, making decisions on their own because waiting for instructions from Earth would be impractical. Future missions to distant worlds will need even smarter AI to handle the lag, but here's a mind-bending thought. What if we're not the only ones facing this problem? Any alien civilization trying to reach out across the galaxy would hit the same light-speed wall. A message from a planet 1,000 light-years away would mean we're hearing voices from a civilization that might have risen and fallen long before humans even built the pyramids. It's a humbling reminder that light speed doesn't just limit our technology, it defines the very rhythm of cosmic conversation. Up next, we'll explore how some of the universe's most violent explosions ride this ultimate speed limit to deliver their spectacular light shows across the cosmos. Now let's turn our attention to one of the universe's most spectacular light shows, gamma-ray bursts. These cosmic explosions are so powerful that for a few fleeting seconds they outshine entire galaxies. And here's the kicker. Their deadly jets race across space at the speed of light, carrying enough energy to vaporize anything in their path. Gamma-ray bursts are the universe's ultimate fireworks, born from the collapse of massive stars or the collision of neutron stars. When these cataclysmic events happen, they fire off narrow beams of high-energy radiation that zip through the cosmos at light speed. Even from billions of light-years away, we can detect their blinding flashes like spotting a lighthouse from across an ocean, but don't let their beauty fool you. If one of these bursts happened too close to Earth, it could strip away our ozone layer and trigger mass extinctions. Thankfully, the nearest known gamma-ray burst was so distant that its light took over 2 billion years to reach us. That's the strange duality of light speed. It delivers both awe-inspiring cosmic spectacles and a built-in safety net, keeping us just out of harm's way. What's truly mind-blowing is that when we detect one of these bursts, we're essentially looking back in time. The light from the most distant ones has traveled for over 13 billion years, offering us a glimpse into the universe's violent youth. It's like unearthing a fossil, but instead of bones, we're studying the afterglow of a star's final scream. Up next, we'll dive into the wild world of theoretical physics, where scientists dream of bending the rules of light speed itself. Now let's shift gears from cosmic explosions to something straight out of science fiction: warp drives. Imagine bending the fabric of space itself to outpace light without breaking the rules of physics. That's the daring idea behind the Alcubierre drive, a theoretical concept that could one day make interstellar travel a reality. Here's how it works. Instead of moving through space faster than light, this hypothetical engine would compress space in front of it and expand space behind it, effectively creating a bubble where the ship rides a wave of warped spacetime. Inside this bubble, the ship wouldn't be moving at all relative to its local space, meaning no pesky relativistic effects like time dilation. It's like stepping onto a moving sidewalk while standing still. The universe does the heavy lifting. But before you start packing for Alpha Centauri, there's a catch. The Alcubierre drive requires exotic matter with negative energy density, something we've never observed in nature. Recent experiments with quantum mechanics hint at tiny amounts of negative energy, but scaling that up to warp drive levels is like trying to power a city with a single A battery. Plus, the energy demands are astronomical, potentially needing the equivalent of Jupiter's mass converted entirely into fuel. Despite these hurdles, scientists haven't given up. NASA Eagleworks lab has explored miniature versions of warp fields, and breakthroughs in quantum physics keep the dream alive. For now, though, warp drives remain firmly in the realm of speculation. A thrilling reminder that even light speed's limits might one day be more flexible than we think. Next up, we'll explore a real-world phenomenon where particles actually do outpace light, at least in certain materials, creating an eerie glow that's as beautiful as it is bizarre. Now let's step into the strange world where particles actually cheat light speed, at least inside certain materials. Picture this, a ghostly blue glow pulsing through the water of a nuclear reactor, like something out of a sci-fi movie. This isn't special effects, it's Cherenkov radiation, nature's version of a sonic boom for light. Here's the twist: while nothing can outpace light in a vacuum, light slows down when it passes through substances like water or glass. That means speedy particles, like electrons zipping away from a nuclear reaction, can actually overtake light in these environments. When they do, they create a shockwave of energy similar to how a jet breaking the sound barrier produces a thunderous boom. But instead of sound, you get that mesmerizing blue shimmer. The color isn't random. Just as a prism splits light into a rainbow, Cherenkov radiation peaks in blue because higher energy light scatters more in water. It's why reactors like those in nuclear power plants or even the cooling pools for spent fuel rods become bathed in that eerie glow. Scientists don't just admire it, they use it to track particle experiments and even detect neutrinos in massive underwater observatories. But here's the real kicker: this phenomenon isn't just limited to Earth. Astronomers suspect Cherenkov radiation might flicker in the icy oceans of moons like Europa, where charged particles from Jupiter's magnetic field could slam into the water. Who knew braking lights' local speed limit could be so useful or so beautiful? Up next, we'll see how light speed isn't just a cosmic curiosity. It's the very ruler astronomers used to measure the universe. Now let's zoom out from those shimmering reactor pools and into the vast cosmic ocean, where light speed becomes the ultimate measuring tape for the universe. Imagine trying to map a continent with nothing but a ruler. It's impossible without scaling up. That's exactly why astronomers rely on light years and parsecs, units stitched together by the steady pace of light itself. Here's how it works. A light year is the distance light travels in 1 year, about 9.5 trillion kilometers, but it's more than just a number. Every time you look at the stars, you're peering into a time machine. The light from Proxima Centauri, our nearest stellar neighbor, takes over 4 years to reach us. The Orion Nebula, that glow left its source 1,300 years ago. Even the Andromeda Galaxy's light is 2.5 million years old by the time it hits your eyes. Now meet the parsec, a trickier but equally vital tool. Picture Earth orbiting the Sun. A star 1 parsec away shifts its position by 1 arcsecond in the sky over 6 months. That's like spotting a coin moving 2 kilometers away. This geometric dance lets astronomers triangulate distances far beyond our solar system. But here's the wild part: ancient thinkers like Aristotle believed starlight reached us instantly. No delay, no cosmic history, just a static, unchanging sky. Today, we know better. The finite speed of light means every observation is a snapshot from the past. When astronomers study distant galaxies, they're literally assembling a cosmic scrapbook, page by page, written in light. And this isn't just academic. The cosmic distance ladder, built on light years, parsecs, and other rungs like Cepheid variable stars, lets us measure everything from nearby exoplanets to the edge of the observable universe. Without understanding light speed, we'd be lost in space, with no way to gauge the scale of our own cosmic backyard. Next up, we'll meet the universe's most precise timekeepers, pulsars, whose light speed beams act like celestial metronomes. Now let's turn our attention to one of the universe's most mesmerizing timekeepers, pulsars. These spinning neutron stars are nature's ultimate lighthouses. sending out beams of radio waves at the speed of light with such precision they rival atomic clocks here on Earth. Born from the explosive deaths of massive stars, pulsars pack more mass than our Sun into a sphere no wider than a city. As they rotate, their intense magnetic fields funnel radiation into narrow beams that sweep across space like cosmic searchlights. When these beams point toward Earth, we detect them as rapid, rhythmic pulses, some flashing hundreds of times per second. What makes pulsars extraordinary isn't just their speed, but their reliability. The fastest, called millisecond pulsars, spin so steadily that their pulses arrive with accuracy better than 1 part in a quadrillion. Astronomers use them as galactic GPS, mapping gravitational waves and even testing Einstein's theory of relativity. When binary pulsars orbit each other, their decaying orbits match relativity's predictions down to the millisecond, proving spacetime really does warp under gravity's grip. But pulsars aren't just scientific tools, they're also cosmic survivors. Some endure in hostile environments, like the pulsar at the heart of the Crab Nebula, which powers the entire nebula's glow. Others, like the famous Hulse-Taylor pulsar, have given us Nobel Prize-winning insights into gravity itself. Next time you gaze at the night sky, remember, hidden among the stars are these natural metronomes ticking away with light-speed precision, quietly shaping our understanding of the universe's deepest laws. And speaking of cosmic clocks, let's explore how black holes manipulate light itself in ways that defy intuition. Now let's unravel one of the most mind-bending tricks the universe plays on our eyes, the frozen star illusion. Picture an astronaut plunging toward a black hole's event horizon, the point of no return. To a distant observer, something bizarre happens. The astronaut seems to slow down, then freeze in place as if time itself has stopped. But here's the twist, it's not real. It's a cosmic sleight of hand caused by light's finite speed. As the astronaut falls closer to the black hole, gravity stretches the light they emit into longer, redder wavelengths. The light takes longer and longer to escape the intense gravitational pull, so each photon reaching our eyes carries a timestamp from further back in the astronaut's journey. From our viewpoint, their final moments stretch into eternity, their image fading into infrared oblivion. Meanwhile, from the astronaut's perspective, they cross the horizon in an instant, torn apart by tidal forces, a grim reality hidden by the universe's light-speed delay. This illusion isn't just a black hole quirk. It's a profound demonstration of how light speed shapes our perception of reality. Even the most extreme events in the cosmos are filtered through the finite pace of light, forcing us to question what we truly see. And while the astronaut's fate is sealed, their frozen image lingers as a haunting reminder of relativity's power to warp time itself. But this is just the beginning of light's strange behavior near black holes. Next, we'll explore how these cosmic monsters don't just trap light, they bend it into impossible shapes. Now let's zoom out from black holes and into the grand tapestry of the cosmos itself, where light speed played a starring role in shaping the universe's very fate. Picture the infant universe just 380,000 years after the Big Bang, a searing plasma of particles and radiation. Then, in a cosmic blink, everything changed. As the universe cooled, light finally broke free from the chaos, creating the first glow we now call the cosmic microwave background. But here's the twist, this afterglow is eerily uniform, with temperatures varying by less than 1 part in 100,000 across the sky. How light speed holds the key. In those early moments, light's finite speed acted like a universal mixing spoon. Regions too far apart to exchange heat or information suddenly could, because light traveling at its ultimate speed had just enough time to connect them before the universe became transparent. This thermal handshake smoothed out temperature differences, leaving behind the nearly flawless cosmic microwave background we observe today. Without light speed setting this cosmic deadline, the universe might have remained a patchwork of hot and cold, altering the birth of galaxies and even the existence of life itself. But light speed didn't just shape the past, it's still writing the universe's future. That same uniformity seeded the vast cosmic web we see now, where galaxies cluster along invisible threads. And as the universe expands, light speed ensures we'll only ever see a fraction of it, a cosmic horizon hiding realms forever beyond our view. So every time astronomers study that ancient glow, they're decoding light speed's signature on reality, a reminder that even the universe's fate hinges on this unbreakable speed limit. Up next, we'll venture into the realm of hypothetical particles that dare to defy this limit, tachyons, the universe's ultimate speed rebels. Now let's step into the realm of cosmic rule breakers, particles that laugh in the face of Einstein's speed limit. Imagine a universe where some particles don't just approach light speed but blast right past it like a race car with no brakes. These are tachyons, the universe's ultimate speed demons. Unlike everything else we know, tachyons wouldn't just flirt with light speed, they'd be born faster than light and couldn't slow down to anything less. Picture a particle that's eternally stuck in overdrive, zipping through space so fast it's already gone before you've even spotted it. But here's the catch, tachyons probably don't exist. While they're a fun thought experiment for physicists, they come with a suitcase full of paradoxes. For starters, if tachyons were real, they'd violate causality, the bedrock rule that cause comes before effect. Imagine a tachyon signal reaching you before it was even sent, like getting a text message before your friend typed it. That's not just weird, it's universe-breaking. Relativity tells us that faster-than-light travel could twist time into pretzels, allowing scenarios where you could theoretically prevent your own birth. So why do scientists still toy with the idea? Tachyons pop up in certain corners of quantum field theory as mathematical quirks, hints that our equations might be missing something. Some theories even suggest tachyons could have played a role in the universe's early expansion, briefly existing before vanishing like cosmic phantoms. But until someone spots a tachyon's telltale signature, perhaps an impossible particle streak in a detector, they'll remain in the realm of tantalizing what-ifs. For now, tachyons serve as a reminder that the universe guards its speed limit fiercely. Even in our wildest theories, light speed stands as the ultimate enforcer, keeping reality from unraveling into chaos. And that's not just physics, it's cosmic law. Next up, we'll tackle a very real challenge born from light speed's stubborn limits, the frustrating delays plaguing our missions to Mars. Now let's shift gears to a very real-world consequence of light speed's unbreakable rule, the frustrating delays that plague our conversations with Mars. Picture this, you're sending a text to a friend, but instead of an instant reply, you're left staring at your phone for up to 22 minutes. That's exactly what Mission Control faces every time they communicate with rovers like Perseverance. The reason: Mars and Earth are constantly playing a cosmic game of tag as they orbit the Sun. At their closest, they're about 33 million miles apart, a distance light takes just over 3 minutes to cross. But when they're on opposite sides of the Sun, that gap balloons to 250 million miles, stretching the one-way light travel time to a sluggish 22 minutes. That means a simple drive forward command could take nearly an hour to receive a confirmation. So how do rovers cope with this agonizing lag? They're designed to think for themselves. Perseverance isn't just a remote-controlled car. It's a rolling robot geologist with enough onboard intelligence to navigate hazards, select rocks for study, and even clean its own cameras. Engineers upload daily to-do lists packed with prioritized tasks, and the rover executes them autonomously, adjusting in real time to surprises like dust devils or tricky terrain. This semi-autonomy is crucial when every second counts. During the nail-biting 7 minutes of terror landing phase, for instance, the rover had to make split-second decisions without Earth's input, because by the time Mission Control saw the parachute deploy, Perseverance had already been on the ground for minutes. Light speed's delay isn't just a technical hiccup, it's a humbling reminder of the vastness of space. even our most advanced machines must operate on cosmic time, where patience isn't just a virtue, it's baked into the laws of physics. Next, we'll peer even deeper into the past, thanks to a telescope that turns light's finite speed into a time machine, shifting our gaze from the red sands of Mars to the deepest corners of the cosmos. Let's unravel one of light's most extraordinary tricks, its ability to turn telescopes into time machines. When Hubble peers at a galaxy 10 billion light-years away, it's not just capturing an image of distant space, it's opening a window into the universe's past. The light hitting Hubble's mirrors today began its journey before Earth even existed, showing us that galaxy as it was in its infancy. This cosmic time travel works because light doesn't reach us instantly. Just as sunlight takes 8 minutes to brighten our skies, the light from distant galaxies takes millions or even billions of years to cross the void. The farther Hubble looks, the further back in time it sees. That stunning ultra-deep field image, for instance, contains galaxies so remote that their light has been traveling for over 13 billion years, snapshots from when the universe was less than 5% of its current age. But here's the mind-bending part. Some of those galaxies might not even exist anymore. Stars could have burned out, collisions might have reshaped them, yet their light lingers like echoes. Hubble's observations reveal cosmic evolution in action, showing us how galaxies grow from small, chaotic clumps into the majestic spirals and ellipticals we see nearby. This time machine effect isn't just poetic, it's foundational to astronomy. By comparing ancient galaxies to modern ones, scientists piece together the universe's life story, from its fiery beginnings to the structured cosmos we inhabit today. Every photon Hubble collects is a puzzle piece in that grand narrative, proving that light speed doesn't just govern space, it stitches together the fabric of cosmic history. Next, we'll explore an even wilder twist in light's timeline, a moment when the universe itself might have outrun its own glow. Now, let's rewind the cosmic clock to the universe's earliest moments, when the rules of light speed played a game of cosmic hopscotch. Picture this: less than a trillionth of a second after the Big Bang, the entire universe underwent a growth spurt so violent it would make even light seem sluggish. Scientists call this inflation, a fleeting era when space itself expanded faster than light could chase it. Here's the wild part: this wasn't a violation of Einstein's cosmic speed limit. Nothing was moving through space faster than light. Instead, space was stretching, carrying galaxies, or rather, their tiny seeds, apart like raisins in rising dough. This explosive expansion helps solve two cosmic mysteries: why the universe looks so uniform in all directions, and why its curvature appears flat. Regions too distant to have ever exchanged light, let alone heat, somehow share the same temperature, a clue that they were once neighbors before inflation flung them apart. But how do we know this happened? The cosmic microwave background, the afterglow of the Big Bang, holds the receipts. Its near-perfect uniformity, down to 1 part in 100,000, is like finding identical snowflakes across an entire continent. Only inflations faster than light stretching could have smoothed the universe so thoroughly, and those tiny fluctuations in the background, they're the quantum seeds inflation magnified into galaxies. This theory isn't just about the past, it reshapes our future. If inflation happened once, could it happen again? Some theories suggest our universe might be one bubble in a frothy multiverse, where other bubbles inflate with entirely different laws. For now, inflation remains the best explanation for why light speed, though unbeatable in a race, couldn't stop space from winning the ultimate cosmic tug-of-war. Next, we'll witness another triumph of light speed, this time as the universe's most reliable messenger. Now, let's turn our attention to one of the most thrilling confirmations in modern physics: gravitational waves, the universe's own ripple effect. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by detecting these faint tremors in spacetime itself. caused by two black holes colliding over 1 billion light-years away. But here's the cosmic kicker. Those ripples raced across the universe at the speed of light, just as Einstein predicted over a century ago. Think of space-time as a vast, invisible trampoline. When massive objects like black holes spiral into each other, they send out waves, warping the fabric of reality like a pebble dropped in a pond. What LIGO captured wasn't just proof of Einstein's genius, it was a direct measurement of gravity's speed. The waves arrived right on schedule, matching light's pace down to the tiniest fraction. This wasn't just a win for relativity, it opened a whole new way to explore the cosmos. Before LIGO, astronomers relied almost entirely on light visible, X-ray, radio to study the universe. But gravitational waves let us hear events invisible to telescopes, like black holes merging in perfect darkness. And because they travel at light speed without slowing down, they carry pristine information across billions of years. When two neutron stars collided in 2017, gravitational waves and gamma rays arrived at Earth within seconds of each other, a cosmic coincidence that sealed light speed's role as gravity's twin. This discovery also solved a lingering mystery: why gravity doesn't seem to have a particle like light's photon. The answer: gravity doesn't need one. Its waves are the fabric of space-time itself in motion, a symphony written in the language of light speed. Every merger LIGO detects is another note in that symphony, reminding us that even in the darkest corners of the universe, light speed still calls the shots. Next up, we'll meet the universe's own speed demons, particles that come shockingly close to outpacing light itself now. Let's zoom in on nature's own particle accelerators, cosmic rays, the universe's high-speed bullets. These aren't rays at all, but atomic fragments, protons, and heavier nuclei hurtling through space at nearly the speed of light. Some reach an astonishing 99.9% of light speed, making them the fastest massive particles we've ever detected. Where does this incredible energy come from? Supernova, the explosive deaths of massive stars. When a star goes supernova, it blasts out shock waves that act like cosmic slingshots, flinging particles to velocities almost indistinguishable from light itself. Imagine a pebble caught in a hurricane, but instead of wind, it's riding a wave of pure stellar fury. Here's where it gets wild. When these particles collide with Earth's atmosphere, they create cascades of secondary particles like a high-energy fireworks display. Scientists detect these showers using ground-based observatories, piecing together the cosmic rays' origins. The craziest part, some ultra-high-energy cosmic rays pack the punch of a fast-pitched baseball, but in a single subatomic particle. That's energy levels 1,000,000 times beyond what our most powerful particle colliders can produce. Yet even at these extreme speeds, cosmic rays obey Einstein's ultimate speed limit. They come agonizingly close to light speed but never quite surpass it. That tiny fraction they're missing, that's relativity's iron grip on the universe. Every cosmic ray is a reminder that no matter how powerful nature's engines are, light speed remains the unbreakable rule. Next, we'll confront a haunting question: why the universe seems so silent, and how light speed might be hiding answers. But here's something to ponder: what if the universe isn't silent at all? What if we just haven't heard anything yet because of light speed's stubborn limits? This brings us to Fermi's paradox, the puzzling contradiction between the high probability of alien civilizations and our complete lack of contact with them. One compelling answer lies in the sheer scale of space and the speed of light. Even if intelligent life is out there, their signals, whether radio waves or laser pulses, travel at light speed. That means a civilization just 100 light-years away would have had to send a message a century ago for us to receive it today, and if they're farther. The delay stretches into millennia. Think of it like this: imagine shouting across a canyon, but the sound takes years to reach the other side. By the time your echo returns, you might have already left. Now scale that up to galactic distances. The Milky Way alone is 100,000 light-years wide, a signal from the far side would take longer to reach us than modern humans have existed. And here's the twist. The universe is 13.8 billion years old, but Earth's been broadcasting detectable signals for barely a century. Our radio bubble is tiny, just a blip in the cosmic ocean. Any alien signals might still be en route, or perhaps they've already passed us by unnoticed. So the great silence, it might not be silence at all. It could just be a matter of waiting or listening in the right way. Which makes every search for extraterrestrial intelligence a race against light speed's delays. Next, we'll unravel another light speed puzzle: quantum tunneling's eerie illusion of breaking the cosmic speed limit. Now, let's shift gears to one of quantum mechanics' most head-scratching phenomena: quantum tunneling. At first glance, it seems like particles pull off a magic trick, slipping through barriers faster than light. But don't be fooled. This isn't a cosmic loophole, it's a quantum quirk that plays by the rules. Here's how it works. Imagine a ball rolling toward a hill. In the everyday world, if the ball doesn't have enough energy, it'll roll back down. But in the quantum realm, particles like electrons can sometimes appear on the other side of that hill as if they teleported. This isn't science fiction, it's called tunneling, and it's why your computer's transistors function and how the sun's fusion reactions ignite. The catch: while tunneling looks instantaneous, it doesn't actually break light speed. Here's why. Quantum mechanics deals in probabilities, not certainties. A particle doesn't physically zoom through the barrier. It's more like the barrier's height becomes fuzzy at tiny scales, giving the particle a chance to show up on the other side without ever crossing the middle. No information travels faster than light, so causality stays intact. Scientists have tested this rigorously. In experiments, even when particles tunnel seemingly faster, any attempt to use this for sending messages fails. The math always balances out, preserving Einstein's cosmic speed limit. So while tunneling bends intuition, it doesn't bend relativity. Up next, we'll dive into the surprising slowdown of light in fiber optic cables, where even the universe's speedster hits traffic. Now, let's take a closer look at something that might surprise you. Light doesn't always race through space at its top speed. In fact, when it's traveling through fiber optic cables, the very backbone of our internet, light slows down significantly. Here's the fascinating part. In a perfect vacuum, light zips along at its maximum speed, 299,792 kilometers per second. But the moment it enters a fiber optic cable, it hits a speed bump. The glass or plastic inside these cables has a higher refractive index, meaning light interacts with the material's atoms, causing it to travel about 30% slower. That's why your video call might still lag, even though light itself is incredibly fast. This slowdown isn't just a quirk, it has real-world consequences. Undersea data cables, which stretch across ocean floors connecting continents, rely on pulses of light to transmit information. But because light moves slower in these cables, signals take slightly longer to travel vast distances. That tiny delay adds up, creating what we call latency. So when you're streaming a movie or playing an online game, those milliseconds matter more than you might think. But here's the clever part. Engineers optimize fiber optics to minimize this slowdown. By using ultra-pure glass and precise angles, they keep light bouncing efficiently down the cable, ensuring data travels as quickly as possible. It's a delicate balance between speed and practicality, because while light in a vacuum is unbeatable, we need fiber optics to keep the world connected. Next up, we'll explore a cosmic time capsule, how the iconic pillars of creation might already be gone, even as their light continues to reach us now. Let's turn our gaze toward one of the most breathtaking sights in the cosmos, the pillars of creation. This iconic image, captured by the Hubble Space Telescope, reveals towering columns of gas and dust where new stars are born. But here's the twist: what we're seeing isn't the present. It's a snapshot from 6,500 years ago. That's because the pillars lie 7,000 light-years away, meaning the light reaching us today began its journey when humans were first building civilizations. And there's a haunting possibility. By now, these majestic structures might already be gone. Astronomers suspect a nearby supernova's shockwave could have shattered the pillars long before their light even reached Earth. Think of it like watching a fireworks display from miles away. You see the explosion, but by the time the sound reaches you, the moment has already passed. Similarly, we're witnessing the pillars' ancient glory, unaware of their current fate. It's a stark reminder that the universe is always in motion, and light speed dictates how we perceive its story. Yet, even if the pillars have vanished, their legacy endures. The image continues to inspire, teaching us about star formation and the fragile beauty of cosmic structures. And who knows, someday, light from their destruction may finally arrive, giving us a front-row seat to their dramatic end. Next, we'll dive into how light speed plays a surprising role in nuclear fusion, where scientists harness its power to recreate the energy of stars right here on Earth. Now, shifting our focus from the vastness of space to the cutting-edge labs here on Earth, let's explore how light speed becomes a crucial tool in humanity's quest to harness the power of stars. At the heart of nuclear fusion research lies a mind-bending technique called inertial confinement fusion, where scientists use lasers traveling at the speed of light to recreate the extreme conditions found in the cores of stars. Here's how it works. Tiny pellets of hydrogen fuel, no bigger than a peppercorn, are bombarded by an array of ultra-powerful lasers. These lasers deliver their energy in pulses so brief, just billionths of a second, yet so intense that they vaporize the pellet's outer layer instantly. The reaction happens at light speed, creating an explosive force that compresses the remaining hydrogen to densities and temperatures rivaling those inside the Sun. This process mirrors what happens in stellar cores, where gravity crushes hydrogen atoms together until they fuse into helium, releasing colossal energy. But here's the catch: while stars have gravity to do the heavy lifting, we rely on light itself. The precision required is staggering. The lasers must strike the pellet symmetrically, with timing accurate to within a trillionth of a second, or the compression fails. The challenge doesn't end there. Even with light-speed lasers, maintaining the reaction long enough to produce more energy than it consumes remains a hurdle. Yet breakthroughs like the National Ignition Facility's 2022 milestone, where fusion briefly generated more energy than the lasers used, show just how close we're getting. What makes this even more remarkable is the cosmic irony at play. We're using light, the very thing bound by universal speed limits, to unlock energy that could one day propel us beyond those limits. It's a testament to human ingenuity, turning a fundamental constraint into a tool for transformation. Up next, we'll unravel the mystery of the WOW signal, a radio burst from deep space that traveled at light speed for 220,000 years, only to leave us with more questions than answers. Now let's turn our attention from Earth laboratories to the depths of space, where a single mysterious signal has baffled scientists for decades. On August 15, 1977, a radio telescope in Ohio picked up something extraordinary, a 72-second burst of radio waves so powerful that astronomer Jerry Amon circled it on the printout and wrote, "Wow," next to it, giving the signal its iconic name. What made this signal so special? For starters, it was narrowband, meaning it was concentrated at one specific frequency. Just what you'd expect from an artificial source, not natural cosmic phenomena. Even more intriguing, it matched the predicted signature of an interstellar transmission, arriving at the hydrogen line frequency of 1420 MHz, a logical choice for any civilization trying to communicate across the cosmos. Here's where light speed comes into play. By the time the WOW signal reached Earth, it had been traveling through space for roughly 220,000 years. That means when this signal began its journey, modern humans were just beginning to spread across the planet. the sheer distance it covered passing through star systems, nebulae, and who knows what else only adds to the mystery. Despite decades of searching, the signal never repeated. Was it a fleeting cosmic accident like a passing comet reflecting sunlight? Or could it have been a deliberate broadcast from an advanced civilization, their message lost in the vastness of space before we could reply? The frustrating truth is we may never know, but the WOW signal remains a tantalizing reminder of light speed's role as both a messenger and a barrier, delivering cosmic secrets while keeping the universe's greatest mysteries just out of reach. Next, we'll dive into another cosmic speed puzzle: why the light from a supernova reaches us instantly, while its thunderous sound takes millennia to arrive. Now, let's shift our cosmic perspective to one of the universe's most dramatic events, a supernova explosion, and uncover the strange disconnect between what we see and what we hear. When a massive star collapses and detonates as a supernova, it unleashes a blinding flash of light and a colossal shockwave ripping through space. Here's the twist: while the light reaches us almost instantly across vast distances, the sound of that explosion lags behind by millennia. Why this staggering delay? It all comes down to the fundamental difference between light and sound in the vacuum of space. Light, being an electromagnetic wave, zips through the cosmos at its famous speed of 299,792 kilometers per second. That means when a supernova erupts in a galaxy 100,000 light-years away, its light crosses that distance in, you guessed it, 100,000 years. But here's the catch: we see it the moment that light finally arrives at Earth, making the event feel immediate to our eyes. Sound, on the other hand, is a pressure wave that needs a medium to travel, like air, water, or even the sparse gas between stars. In the near-perfect vacuum of space, there's almost nothing for sound to push against, so those supernova shockwaves crawl across the cosmos at a snail's pace compared to light. Even when they do encounter pockets of interstellar gas, the sound waves move at mere kilometers per second, taking tens of thousands of years longer than light to cover the same distance. Imagine witnessing a supernova from a safe distance. Your eyes register the brilliant flash in an instant, but if you could somehow hear it, you'd be waiting longer than all of recorded human history for the sound to arrive. This bizarre mismatch isn't just a cosmic curiosity, it's a reminder of how light speed shapes our perception of the universe. We're essentially time travelers, seeing violent stellar deaths as they happened millennia ago, while their echoes still reverberate silently through the void, unheard and unnoticed. Next, we'll tackle a subtle but mind-bending question about light speed itself, whether it truly moves at the same pace in every direction, or if Einstein's theory might have a hidden loophole. Now, let's peel back another layer of light's mysteries, one that even Einstein's theory leaves slightly open to interpretation. Here's a question that might seem simple but has baffled physicists for decades. Does light really travel at the same speed in every direction, or could there be a hidden asymmetry in the cosmos? At first glance, the answer seems obvious. Einstein's theory of relativity treats the speed of light as a universal constant, 299,792 kilometers per second in a vacuum, no matter which way you're looking. This assumption is baked into everything from GPS satellites to our understanding of the Big Bang. But here's the twist: we've never actually proven that light speed is identical in all directions. It's a subtle loophole that's surprisingly hard to test. Think of it like this: imagine you're sending two beams of light, one east and one west, to mirrors exactly 1 kilometer away. If both beams return at the same time, you'd assume they traveled at identical speeds. But here's the catch: what if one beam was slightly faster on its outbound journey and slower coming back? The round-trip average would still match the expected speed, masking any one-way difference. This is the core of the debate. All our measurements of light speed rely on round-trip experiments, leaving the one-way speed fundamentally unverified. Some physicists, like Nobel laureate Richard Feynman, have called this a convention rather than a law, a useful assumption that keeps the math tidy. Others have proposed exotic theories where light speed varies with direction, potentially hinting at undiscovered physics. But here's why it matters. If light did have a directional speed bias, it could reshape our understanding of spacetime, challenge the symmetry of relativity, and even alter how we calculate distances to faraway galaxies. For now, the one-way speed of light remains a fascinating what-if in physics, a reminder that even our most trusted cosmic rules might have hidden wrinkles waiting to be ironed out. Up next, we'll explore how Einstein used a simple elevator to reveal light's intimate dance with gravity. Now, let's step into Einstein's imaginary elevator for a mind-bending demonstration of how light and gravity intertwine. Picture this: you're in a windowless elevator drifting through space far from any planet's pull. Suddenly, the elevator accelerates upward. Inside, you'd feel a force pinning you to the floor, just like gravity on Earth. But here's where light enters the scene. If you shine a beam of light horizontally across the elevator, something extraordinary happens. As the elevator accelerates, the light's path appears to curve downward. Why? Because while the light travels straight, the elevator moves upward during that tiny fraction of a second, making the beam seem to bend. Einstein realized this wasn't just a trick of perspective. Acceleration and gravity produce identical effects on light, a cornerstone of his general theory of relativity. On Earth, gravity bends starlight passing near the sun, just as the accelerating elevator bent the light beam. This equivalence solves cosmic puzzles, like why light redshifts when climbing out of a gravitational well. The energy it loses mirrors the Doppler effect of a receding sound wave. But the real magic is how this thought experiment reshaped physics. It revealed that gravity isn't a force tugging on objects, but the warping of spacetime itself. Massive objects like stars dent spacetime, and light simply follows these curves like a marble rolling along a stretched bedsheet. Next time you're in an elevator, remember, Einstein turned this everyday experience into a portal to understanding the universe's deepest workings. Up next, we'll unravel how quantum teleportation plays by light speed's rules without breaking them. Now, let's shift gears to something that sounds like pure science fiction but is very real: quantum teleportation. Here's the twist: it doesn't involve zapping objects across space like in movies. Instead, it's all about transferring quantum information instantly between entangled particles, all while playing by light speed's rules. Imagine two particles, like electrons or photons, that become entangled. No matter how far apart they are, whether across a lab or across the galaxy, their properties remain mysteriously linked. Change one and the other changes too, instantly. This might seem like faster than light communication, but here's the catch: you can't use this link to send actual messages or data faster than light. Why? Because to make sense of the teleported information, the sender and receiver still need to exchange classical details, like a key to decode the quantum signal, and that exchange is limited by light speed. This process, called quantum teleportation, is like mailing a locked box with the contents already inside. The box itself arrives instantly thanks to entanglement, but the key to open it, that still has to travel the old-fashioned way at light speed. Scientists have already pulled this off over distances of hundreds of miles, with potential applications in ultra-secure quantum communication and computing. So while quantum teleportation bends our intuition, it never breaks the universe's ultimate speed limit. It's a brilliant workaround that keeps Einstein's relativity intact while opening doors to technologies we're only beginning to imagine. Up next, we'll peer into the past as we explore how the light from Andromeda shows us a snapshot from before humans even walked the Earth. Now, let's take a cosmic step back in time, because when you gaze at the Andromeda galaxy, you're not seeing it as it is today, but as it was 2.5 million years ago. That's how long its light has been racing across space to reach your eyes. Picture this: while that light was mid-journey, Earth's earliest human ancestors were just beginning to walk upright. The Andromeda Galaxy, our Milky Way's closest spiral neighbor, sits a staggering 2.5 million light-years away. Every photon hitting your retina is a relic from an era when mastodons roamed and continents looked wildly different. This time delay isn't just a cool trivia fact, it's a fundamental quirk of astronomy. The deeper we peer into space, the further back in time we see. Andromeda's light-speed snapshot reveals a galaxy untouched by human existence, its stars and dust frozen in a moment our species wouldn't witness for millennia. Even more mind-bending, if aliens in Andromeda had powerful telescopes pointed at Earth right now, they'd see African savannas dotted with early hominins, not skyscrapers or satellites. This cosmic time machine effect isn't unique to Andromeda. It applies to everything we observe in the universe. But what makes Andromeda special is its proximity. It's the farthest object you can see with the naked eye on a clear night, a faint smudge that's actually a window to prehistory. So next time you spot it, remember, you're not just stargazing. You're time traveling. Up next, we'll shift from looking back to leaping forward with solar sails that could one day propel tiny spacecraft at a fifth of light speed. Now, let's turn our gaze from the distant past to the cutting edge of future space travel, where light itself becomes the engine. Imagine spacecraft so lightweight and fast they could reach 20% of light speed, not with rockets but with sails pushed by lasers. This isn't science fiction, it's the ambitious vision behind projects like Breakthrough Starshot. The idea is simple yet revolutionary: tiny nanocrafts no heavier than a paperclip, equipped with ultra-thin reflective sails. Instead of burning fuel, they'd be propelled by powerful Earth-based lasers firing concentrated beams of light. Photons, though massless, carry momentum, and when they bounce off these sails, they transfer that momentum, gently but relentlessly accelerating the craft. Over minutes, this laser push could theoretically propel these probes to speeds surpassing any chemical rocket, up to 134 million miles per hour. Why aim for such blistering speeds? Because even at 20% of light speed, reaching our nearest star system, Alpha Centauri, would take just over 20 years, a blink compared to the tens of thousands of years traditional rockets would require. Breakthrough Starshot's goal is to send a swarm of these nanocrafts, each carrying cameras and sensors, to beam back the first close-up images of an alien world. But the challenges are as extreme as the speeds. The sails must be near-perfect mirrors, reflecting 99.9% of laser light to avoid vaporizing. The lasers themselves would need to be 100 times more powerful than today's most advanced arrays. And steering, once launched, there's no braking or course correction, just a high-speed dash past another star. Yet if it works, humanity could achieve interstellar exploration within a lifetime. Future missions might even use sunlight instead of lasers, with sails kilometers wide catching the gentle push of solar photons, a slower but unlimited propulsion system for touring our own solar system. Up next, we'll see how light speed isn't just a barrier. It's the key to solving one of cosmology's biggest puzzles, the horizon problem. Now, let's unravel one of the most mind-bending implications of light speed, how it holds the key to understanding the universe's very first moments. Picture this: in the tiniest fraction of a second after the Big Bang, the entire cosmos expanded faster than light itself. This wasn't objects moving through space, but space itself stretching at speeds that defy relativity's usual rules. This runaway expansion, called cosmic inflation, solves two cosmic mysteries at once. First, the horizon problem. Why does the universe look so uniform in every direction? If light had only traveled at its fixed speed since the Big Bang, distant regions should never have had time to talk to each other, yet they share the same temperature and structure. Inflation's faster-than-light stretch smoothed everything out in an instant, like pulling on a crumpled sheet. Second, it explains why the universe appears flat. Just as blowing up a balloon makes its surface seem flatter, inflation stretched space so drastically that any initial curvature became imperceptible. Here's the twist: light speed's limit still wasn't broken. Relativity allows space itself to expand without bound, while objects within it stay below light speed. This rapid stretching also planted the seeds for galaxies. Quantum fluctuations, tiny ripples in energy, got magnified to cosmic scales during inflation. Those ripples became the blueprints for stars and galaxies we see today, all because space outran light for a fleeting moment. Without inflation's brief faster-than-light sprint, our universe might look wildly different, lumpy, curved, and full of unexplained gaps. Instead, light speed's delicate dance with expansion gave us the vast, balanced cosmos we call home. Coming up, we'll see how this universal speed limit doesn't just shape space, it also dictates how gravity itself moves through the void. Now, let's shift our focus to another cosmic speedster, gravity itself. You might think of gravity as an invisible force that pulls objects together instantly, but here's the twist: it doesn't work that way. Just like light, gravity has a speed limit, and it moves at exactly the same pace, 299,792 kilometers per second. This revelation came to life in a spectacular cosmic event back in 2017, when two neutron stars collided over 100 million light-years away. As they spiraled toward each other, they sent ripples through the fabric of space-time gravitational waves that raced across the universe at light speed. Meanwhile, the collision also unleashed a burst of gamma rays, the universe's fastest light. Scientists detected both the gravitational waves and the light arriving at Earth within seconds of each other, proving they traveled at the same speed. Why does this matter? Because it confirms one of Einstein's boldest predictions. Gravity isn't some magical, instantaneous force. It's more like a wave in a pond spreading outward at a finite speed. If the sun suddenly vanished, Earth wouldn't fly off into space immediately. Instead, we'd keep orbiting for about 8 minutes, the same time it takes sunlight to reach us before feeling gravity's absence. This cosmic speed limit also solves a puzzle about black holes. When two black holes merge, their gravitational waves carry energy away at light speed, causing the new black hole to recoil. Without this speed limit, the math of relativity would collapse, and the universe's most violent events wouldn't make sense. So next time you feel gravity's pull, remember, it's not just holding you down, it's racing across space at the universe's ultimate speed, weaving the cosmos together one ripple at a time. Up next, we'll see how even the most advanced telescopes rely on light's finite speed to peer back in time, revealing galaxies as they were billions of years ago. Now, let's turn our gaze to one of humanity's most incredible time machines, the James Webb Space Telescope. Unlike ordinary telescopes that capture visible light, Webb specializes in infrared, allowing it to see the universe's oldest, most distant galaxies. But here's the catch: the light from these galaxies has been stretched into the infrared spectrum by the expansion of the universe itself, a phenomenon called redshift. Imagine a cosmic game of telephone where the message light from a newborn galaxy gets distorted over billions of years. As space expands, the light waves traveling through it stretch out, shifting from visible colors to longer infrared wavelengths. Webb's ultra-sensitive instruments catch these faint whispers of light, revealing galaxies as they were just a few 100 million years after the Big Bang. This redshift effect is like a fingerprint of cosmic history. The more stretched the light, the farther and older the galaxy. Some of the light Webb collects has been journeying for over 13 billion years, meaning we're seeing these galaxies not as they are today, but as they were when the universe was in its infancy. What's truly mind-blowing is that without light's finite speed, none of this would be possible. If light traveled instantaneously, we wouldn't have this layered view of cosmic history. Every galaxy, near or far, would appear as it is right now, robbing us of the universe's grand timeline. So when Webb beams back images of swirling primordial galaxies, remember, you're not just looking deep into space, you're peering back in time, thanks to the steadfast speed of light and the relentless expansion of the cosmos. Coming up, we'll dive into the world of particle accelerators, where scientists push protons to within a hair's breadth of light speed, bending the rules of reality itself. Shifting our focus from the vast cosmos to the microscopic world, let's zoom in on humanity's most ambitious speed machines, particle accelerators. Deep beneath the border of France and Switzerland, the Large Hadron Collider, or LHC, whips protons to a staggering 99.999999% of light speed. That's just 3 meters per second shy of the cosmic speed limit. At these extreme velocities, the rules of everyday physics break down. Protons gain so much energy that their mass increases dramatically, a mind-bending effect predicted by Einstein's relativity. Engineers must account for this by strengthening magnetic fields to keep the particles on track. Imagine steering a train that suddenly weighs as much as a mountain. The LHC's collisions are so violent they recreate conditions unseen since the universe's first trillionth of a second. Yet even here, light speed remains the unbreakable barrier. No matter how much energy we pump into these particles, they'll never quite reach that magic number of 299,792 kilometers per second. This relentless pursuit of near-light speeds isn't just about smashing particles, it's a testament to human ingenuity, pushing technology to its limits to unravel the universe's deepest secrets. Next, we'll confront a cosmic puzzle that baffled astronomers for centuries: why the night sky isn't blindingly bright, despite the infinite stars overhead. Now let's unravel one of the cosmos' oldest riddles: why the night sky isn't a blazing sheet of light. This puzzle, known as Olbers' paradox, haunted astronomers for centuries. If the universe were infinite and filled with endless stars, every line of sight should eventually hit a star, bathing Earth in perpetual daylight. Yet our nights remain dark, and the answer lies in the very fabric of light speed itself. First, light takes time to reach us, lots of it. The universe may be vast, but it's not infinitely old. We can only see stars whose light has had enough time to travel across space since the Big Bang, roughly 13.8 billion years ago. Beyond that cosmic horizon, light simply hasn't reached us yet, leaving patches of darkness between the stars. Second, the universe is expanding, stretching light from distant galaxies into invisible infrared wavelengths, a phenomenon called redshift. This steals energy from their glow, dimming their contribution to the sky's brightness. Combine this with the fact that many stars burn out before their light can cross the cosmos, and suddenly the paradox crumbles. So the night sky's darkness isn't just emptiness, it's a cosmic timestamp, a reminder that light speed and the universe's age work together to paint our view of the heavens. Next, we'll dive into the quantum realm, where particles seem to flirt with breaking light speed's rules without ever quite succeeding. Now let's step into the strange world of quantum mechanics, where even empty space isn't truly empty. Here, virtual particles pop in and out of existence in a frenzy of quantum fluctuations, defying our everyday intuition. These fleeting particle pairs, like electrons and their antimatter twins, borrow energy from the vacuum itself, existing just long enough to dance on the edge of reality before vanishing again. What's truly mind-bending is how they play with light speed's rules. While these particles seem to appear and disappear faster than light could travel between them, they never actually break the cosmic speed limit. That's because no real information or energy is being transferred. It's all a temporary loan from the universe's quantum ledger, repaid before causality gets violated. This phenomenon isn't just theoretical. It's the reason your toaster doesn't stick to the fridge. Virtual particles create the Casimir effect, where two metal plates placed microscopically close in a vacuum feel a slight push from the quantum froth outside them. Even black holes exploit this trick, with Hawking radiation relying on virtual particles near the event horizon to slowly bleed energy away. So while these ghostly particles flirt with breaking light speed, they're ultimately bound by the same cosmic laws, just with a quantum twist. Next, we'll tackle a relativity brain teaser where a ladder moving at near light speed defies all common sense about space and time. Now let's stretch our minds with one of relativity's most famous puzzles, the ladder paradox. Picture this: a farmer owns a barn with doors at both ends, and a speedy astronaut races toward it carrying a ladder. Here's the twist: while the ladder is slightly longer than the barn when measured at rest, at near light speeds, something incredible happens. From the farmer's perspective, the ladder contracts due to relativistic length contraction, squeezing short enough to fit entirely inside the barn. For a fleeting moment, both barn doors could even close simultaneously, trapping the ladder inside. But wait, the astronaut sees things completely differently. From their viewpoint, it's the barn that's moving at light speed, so the barn shrinks while the ladder stays its normal length. To them, there's no way the ladder could ever fit inside that tiny, contracted barn. So who's right? This paradox isn't just a clever thought experiment. It reveals the core of Einstein's relativity. Both observers are correct within their own frames of reference because space and time aren't absolute. The solution lies in the relativity of simultaneity. The farmer and astronaut disagree on whether the front and back doors close at the same time. What's simultaneous for one isn't for the other, preserving the laws of physics for both. This bizarre effect isn't just theoretical. Particle accelerators deal with length contraction daily. Protons in the Large Hadron Collider flatten like pancakes as they approach light speed. Next, we'll see how astronomers use light speed's quirks to spot planets orbiting distant stars. Now let's turn our attention to the stars, where light speed becomes a detective's tool in the hunt for alien worlds. Astronomers have discovered thousands of exoplanets, and one of their most powerful techniques hinges on the speed of light itself. Here's how it works. When a distant planet crosses in front of its host star, it blocks a tiny fraction of the star's light, like a moth flitting past a spotlight. But detecting that faint dip isn't just about spotting shadows. It's about measuring the precise timing and depth of that dimming, which depends on light traveling across space at that universal speed limit. The transit method is a cosmic stopwatch. As starlight races toward us at 299,792 kilometers per second, even a millisecond delay or a subtle change in brightness can reveal a planet's size, orbit, and even its atmosphere. For example, when NASA Kepler telescope observed a star dimming by just 0.01%, it signaled a planet roughly the size of Earth. And by analyzing how the star's light filters through a planet's atmosphere during these transits, scientists can sniff out gases like water vapor or methane, clues to potential habitability. But there's a catch. Light speed isn't just a tool, it's also a limitation. The farther away an exoplanet is, the longer we wait for its transits to reach us. Some of the planets we've spotted are hundreds of light years away, meaning we're seeing their transits as they happened when Shakespeare was writing plays. Yet this delay is also a gift. It lets us peer into the past, one photon at a time. Next up, we'll dive into one of spacetime's wildest what-ifs, cosmic strings, theoretical scars from the Big Bang that might twist the rules of light speed itself. Now let's stretch our imaginations to one of the most bizarre possibilities in physics: cosmic strings. Picture the universe just after the Big Bang, a seething cauldron of energy where spacetime itself might have formed tiny cracks like flaws in a frozen lake. These hypothetical cosmic strings are thought to be ultra-thin, infinitely long wrinkles in spacetime, thinner than an atom but denser than a mountain range. And here's where light speed gets twisted. If these strings exist, they could warp spacetime so severely that they'd create shortcuts across the cosmos, like folding a piece of paper to bring two distant points together. Einstein's relativity says nothing can outpace light in normal space, but cosmic strings could bend the rules. Imagine a spaceship traveling near one of these strings. The intense gravitational pull would curve spacetime around it, effectively reducing the distance the ship needs to cover. From an outside perspective, it might seem like the ship moved faster than light, but in reality, it just took a cosmic detour. This isn't breaking the speed limit, it's finding a loophole. The catch: no one's ever detected a cosmic string. They're ghostly relics predicted by theories, like the universe's version of invisible spiderwebs. Some scientists think these strings might reveal themselves through gravitational lensing, distorting light from distant galaxies in strange, telltale ways. Others speculate that if two strings crossed, they could unleash bursts of energy detectable as ripples in the cosmic microwave background. So while warp drives and wormholes dominate sci-fi, cosmic strings offer another tantalizing maybe. They remind us that the universe's rulebook might have pages we haven't read yet, and light speed, that steadfast constant, could have cosmic exceptions waiting to be discovered. Next, we'll revisit a groundbreaking experiment that proved Einstein right, where starlight itself became the key to unlocking gravity's secrets. Now let's turn the clock back to one of the most pivotal moments in science history, a daring experiment that turned starlight into proof. In 1919, British astronomer Arthur Eddington set out to test Einstein's wildest prediction, that gravity could bend light itself, the stage. A total solar eclipse where the moon's shadow would blot out the sun, revealing stars normally hidden in its glare. Einstein's theory claimed the sun's immense gravity would warp spacetime around it, deflecting starlight like a marble rolling past a bowling ball. But skeptics demanded proof. Eddington saw his chance. He led expeditions to Principe Island off Africa and Sobral in Brazil, hauling telescopes and photographic plates into the path of totality. On May 29th, as the eclipse unfolded, his team captured images of stars near the sun's edge. The results were revolutionary. The stars' positions appeared shifted exactly as Einstein's math predicted. Light from those distant suns had curved around the sun's gravitational well, proving spacetime wasn't just a grid but a flexible fabric. Newspapers worldwide declared Einstein a genius overnight, though he quipped, "I would have been sorry for the dear Lord, the theory is correct." This eclipse test didn't just validate relativity, it reshaped how we see the universe. Suddenly, light wasn't just a beam, it was a cosmic traveler, its path twisted by gravity's invisible hand. And that bending, it happens at light speed, no delay, because gravity's influence moves at the same ultimate velocity. So next time you see an eclipse, remember, it's not just a celestial shadow show. It's a reminder that even light, the universe's speedster, must follow gravity's rules, and sometimes the boldest ideas are proven right in the darkest moments. Up next, we'll explore how light-speed photons are revolutionizing the race to build ultra-fast quantum computers. Now let's shift gears to a cutting-edge frontier where light speed meets the quantum realm, the world of quantum computing. While traditional computers rely on electrons buzzing through silicon chips, quantum machines harness something far more elusive: particles of light. Photonic qubits, the building blocks of light-based quantum computers, exploit photons traveling at, you guessed it, the speed of light to perform calculations that would stump even the most powerful supercomputers. Here's why this matters. In conventional computing, electrons face resistance as they move, generating heat and slowing things down. But photons, they zip through fiber optics or even air with zero resistance, carrying information almost instantaneously. Quantum computers using photonic qubits can process complex problems like simulating molecular interactions or cracking encryption, at speeds that leave traditional machines in the dust. Researchers are already achieving breakthroughs. Companies like Xanadu and academic labs are creating quantum processors where entangled photons perform calculations in nanoseconds. Imagine a future where drug discovery, climate modeling, or financial forecasting happens in the blink of an eye, thanks to light's unbeatable pace, but there's a catch. Controlling these speedy photons is like herding fireflies. They're fragile, easily lost or disrupted, requiring ultra-precise lasers and mirrors to keep them on track. Yet every hurdle overcome brings us closer to a revolution where light-speed computing reshapes technology itself. So while quantum computing is still in its infancy, one thing's certain: when photons are your workhorses, the future moves at the speed of light. Up next, we'll venture into one of space's greatest mysteries, a void so vast its light-speed distance defies explanation. Now let's journey into one of the universe's most baffling enigmas, the Boots void. Picture a region of space so staggeringly empty that it defies comprehension. Stretching an astonishing 330 million light-years across, this cosmic desert is nearly devoid of galaxies, making it one of the largest known voids in existence. To put that into perspective, if you could travel at the speed of light, it would take you 330 million years just to cross this vast nothingness. What makes the Boots void so puzzling? Most voids in space are like bubbles in a cosmic foam, surrounded by walls of galaxies, but this one is different. It's not just big, it's too big. Based on our current understanding of the universe's structure, a void this size shouldn't exist. Theories suggest it might be the result of smaller voids merging over billions of years, or perhaps evidence of something even stranger lurking in the fabric of space-time. The sheer scale of this emptiness also plays tricks with light itself. Because of its mind-boggling distance, the light we see from the few galaxies within the void is ancient, a snapshot from an era when the universe was far younger. Some astronomers speculate that the Boots void could be a window into rare cosmic phenomena, like the remnants of a colossal collision between universes in the multiverse. Yet despite its mystery, the void teaches us a humbling lesson. Even at light speed, the universe holds secrets so vast they challenge our very understanding of reality. Up next, we'll explore how light speed could shape the ultimate fate of the cosmos itself. Shifting our gaze to the far future, let's ponder one of cosmology's most dramatic possibilities, the Big Crunch. Imagine a universe where expansion reverses and everything collapses back into a single point. Now, here's the twist. Could the speed of light play a role in this cosmic doomsday? In a Big Crunch scenario, galaxies would hurtle toward each other as space itself contracts. But light's finite speed means we'd see this collapse in slow motion. Distant galaxies would appear frozen in time, their light struggling to reach us as space tightens around them. It's like watching a car crash in ultra-slow motion. The closer the collision, the faster it seems, while distant events fade into an eerie stillness. Some theories suggest light speed might even dictate the crunch's final moments. As matter compresses, photons could be trapped in a shrinking cosmic prison, their energy fueling a fiery finale. Others argue that relativity's rules would bend but not break light speed, remaining the universe's ultimate referee, even as space-time folds in on itself. Yet here's the catch: we don't know if the Big Crunch is real. Dark energy seems to be accelerating expansion, making a collapse unlikely. But if it ever happened, light speed would be the silent witness, shaping how we perceive the universe's last breath. Next, we'll dive into how light speed complicates our hunt for dark matter's elusive particles. Now, let's turn our attention to one of the universe's greatest mysteries, dark matter. This invisible substance makes up roughly 85% of the universe's mass, yet it refuses to reveal itself directly. So how does the speed of light play into our hunt for these elusive particles? Scientists believe dark matter could consist of weakly interacting massive particles, or WIMP, or perhaps even lighter particles called actions. Here's the catch: these particles, if they exist, would interact at or near the speed of light, making them incredibly difficult to detect. Imagine trying to catch a shadow with your bare hands. It moves so fast and slips through your fingers before you even realize it's there. Experiments deep underground, like those in abandoned mines or beneath mountains, are designed to catch rare collisions between dark matter particles and ordinary atoms. But because these interactions would happen at light speed, the signals are faint and fleeting, like whispers in a thunderstorm. Even our most sensitive detectors struggle to pick them up. Some theories suggest actions, if they're real, could transform into photons under strong magnetic fields, giving us a tiny, light-speed glimpse of their presence. Yet so far, every experiment has come up empty. The speed of light isn't just a barrier for travel, it's also a challenge for discovery, keeping dark matter just out of reach. But the search isn't over. New detectors and space telescopes are pushing the limits, hoping to catch even the faintest trace of these ghostly particles. Because if we ever do spot them, it won't just solve a cosmic mystery, it'll rewrite the rules of physics itself. Next, we'll explore how light speed shapes the wild possibilities of the multiverse. Now let's stretch our imaginations beyond the known universe and into the realm of the multiverse. What if the speed of light isn't the same everywhere? In alternate universes, could light zip faster or crawl slower, rewriting the very laws of physics as we know them? Some theories suggest that other universes in the multiverse might operate with entirely different constants, meaning light speed there could be 10 times faster, or a fraction of what it is here. Picture a universe where light moves so sluggishly that a simple beam takes years to cross a room, or one where it flashes by in an instant, making our cosmic speed limit seem quaint. If light speed varied in other universes, the consequences would be staggering. Stars might burn differently, black holes could behave in ways we can't predict, and even time itself might flow at alien rhythms. The familiar equations of Einstein's relativity would crumble, replaced by rules we can barely fathom. Yet here's the twist: even if these alternate universes exist, we'd likely never know. Their light, bound by their own unique speed limits, might never reach us across the vast divides between realities. It's a humbling thought. Our universe's physics might just be one variation in an infinite cosmic symphony, each note playing at its own tempo. So while we chase answers here, the multiverse remains a tantalizing what if, where light speed isn't a universal rule, just a local guideline. Next, we'll reflect on how this constant defines the very fabric of our reality. Now, as we reach the final frontier of our cosmic journey, let's pause to appreciate light speed's profound role as the universe's ultimate rulebook. This single constant, 299,792 kilometers per second, isn't just a number. It's the invisible thread weaving through every law of physics, from the tiniest quantum particles to the vast expanse of galaxies. Think of it as the universe's heartbeat. Without this speed limit, chaos would reign. Atoms wouldn't bond the same way, stars couldn't shine, and time itself would lose its rhythm. Einstein's relativity, quantum mechanics, even the fate of the cosmos all dance to light speed's unyielding tune. It's why we can trust that a second on Earth is the same as a second near a black hole, even if time stretches differently. But here's the beautiful paradox: while light speed confines us, it also connects us. Every photon from a distant star, every ripple of gravity from colliding black holes, even the signals from your phone, all travel at this universal pace, stitching the cosmos into a single, shared reality. It's the reason we can peer billions of years into the past with telescopes, and why the laws of physics feel like home, no matter where we look. So as we close this voyage through light's extremes, remember, this speed limit isn't a barrier, it's the foundation of everything. It's what makes the universe knowable, measurable, and breathtakingly consistent. And who knows, maybe one day we'll uncover even deeper layers to this cosmic constant. Until then, the speed of light remains our guiding star, lighting the way to countless more mysteries waiting in the dark. Thank you for joining this journey through the universe's most astonishing speeds. If your mind is as blown as mine, hit that like button, subscribe for more cosmic adventures, and ring the notification bell so you never miss a launch into the unknown. Drop your favorite fact in the comments. Was it the black holes trapping light or the multiverse's wild possibilities? Until next time, keep looking up. And with that, we've raced through 50 astonishing truths about light speed, each one revealing how this cosmic constant shapes everything from the atoms in your body to the farthest edges of the observable universe. Whether it's black holes bending light into oblivion, entangled particles defying distance, or the eerie glow of Cherenkov radiation, every fact we've explored ties back to that unshakable speed limit, 299,792 kilometers per second. It's the universe's heartbeat, the rhythm that keeps reality in sync. But here's the thrilling part: this isn't the end. Every discovery peels back another layer of mystery. Could warp drives one day bend the rules? Will quantum physics rewrite what we know? The questions are as endless as the cosmos itself. So tell me in the comments, which fact left you starstruck? Was it the frozen stars at a black hole's edge, or the thought that Andromeda's light is a snapshot from before humans even walked the Earth? Before you go, don't forget to like and subscribe if you've enjoyed this lightspeed journey. Hit that notification bell so you're always first to blast off into the next cosmic adventure. Until next time, keep your eyes on the skies because the universe's secrets are waiting, one photon at a time.